Hello everyone and welcome to this channel. If this is your first time here, please subscribe and hit the notification icon so you could be notified on my new weekly videos on MATLAB and MATLAB functionalities for beginners. In today's video, you will learn how to model simple organic Rankine cycle in MATLAB using CoolProp fluid library. I will show you two examples of simple ORC model with R11 and R245fa. You will also learn how to call CoolProp fluid properties and functionalities in MATLAB. Let's jump into this right away. So this is my MATLAB opened. If you're not familiar with MATLAB or you've not used MATLAB before, MATLAB is an acronym for Matrix Laboratory. It is a high programming language developed by MathWorks, and it has interactive environment for numerical computation, data analysis, data processing, and programming. It also has inbuilt functions and toolboxes for you to use, and you can create your own functions from scratch in MATLAB language. I've provided a link below this video to where and how you can download MATLAB and install MATLAB on your computer. Let's get started with the Organic Rankine Cycle. At top level, the Organic Rankine Cycle, ORC, follows similar thermodynamic process as the steam cycle. The major difference between the Organic Rankine Cycle and the steam Rankine Cycle is the working fluid. ORC uses organic fluid as its working media. And you may ask, why organic fluid? Organic fluids are high molecular mass fluid. They have their boiling point and phase change occur at lower temperature than water or steam. This is a schematic representation of a simple Rankine cycle. So a simple Rankine cycle has four major components. You have the pump, you have the evaporator or the boiler, and within this evaporator or the boiler, you have the heat source coming from either the waste heat from an IC engine, from a gas turbine, or it could be a solar heat source. And then you have the turbine and you have the condenser. So the pump raises the pressure of the working fluid into the boiler or the evaporator, and at constant pressure the temperature of the organic fluid is raised and it goes into the turbine where work is extracted from the working fluid. And once it finishes from the turbine, it goes to the condenser for the cooling process, and then the process continues again as a closed cycle loop. I will not go much into details explaining the thermodynamics of the ORC or into the parametric analysis, as my goal in this video is just to show you how to model a simple ORC in MATLAB. So, to model the ORC, first we need to know what type of organic fluid are we using, because every working fluid have their own thermodynamic properties and behavior. So once you know the type of organic fluid that you are using, it helps you to understand the behavior of that organic fluid, and then you can model appropriately. Second, you need to know what are the input parameters. What is the pressure of the working fluid going into the boiler, and possibly what is the temperature of the working fluid leaving the boiler. These are important parameters. And then again, you need to know at what temperature are you cooling the working fluid before it goes back into the pump. And of course, if it's not an ideal process, then you would want to know what is the pump efficiency or what is the turbine efficiency. I've also put down here some key performance indicators that we will be using during the model. The first one here is the heat input, which is a function of the organic fluid mass flow and the enthalpy difference between the turbine inlet and the pump outlet. So we're looking at what enthalpy of the fluid as at when it enters the boiler and as at when it leaves the boiler. That gives us the heat input. Then another parameter we're interested in that we're going to be using in the model is the turbine work. And the turbine work will be a function of the organic fluid mass flow and the enthalpy difference between the inlet of the turbine and the exit of the turbine. And then next, we're also going to calculate the pump work. The pump work, again, is a function of the fluid mass flow and the enthalpy difference between the inlet of the pump and the exit of the pump, which is also a function of the specific volume and the pressure difference between the inlet of the pump and the exit of the pump. And with these two information, we can now calculate the shaft output power, which is the difference between the turbine work and the pump work. And the efficiency is the ratio of the shaft output power and the heat input. Another important parameter we are going to be using is the fluid quality. There are several ways to calculate the fluid quality. But for the purpose of this model, we should be aware of this approach. That is the entropy of the fluid at a particular point, pressure and temperature, and the entropy of the fluid at liquid phase, and the entropy of the fluid at two phase. So we will start with the R11 fluid. This is the TS diagram of R11. So within this line, you have the constant temperature lines going all straight, and then you have the constant pressure lines going this way. So you have the constant temperature lines going this way, all straight. And then you have the constant pressure lines going this way, let's say this, and then once it hits this at the end of this zone here, and then it hits this way. Sorry, I'm not making a straight line, but it just goes all through the straight line are the constant pressure lines. So for any temperature that you're raising the organic fluid to, you need to find what is the corresponding pressure required to raise that working fluid to that temperature. So if this is the case, our goal will be to design or model a system where we can have high efficiency. And to achieve that, we could either drag the temperature to heat somewhere around this dry quality of vapor. So to heat somewhere around here, and from there we can then extract the work from this constant entropy line down, and then whatever temperature we are raising the fluid down to, or we're taking the fluid down to, we can then move to that temperature line. So next, let's define the input parameters for our modeling. For the R11, let's assume that the temperature going into the turbine from the boiler is 460 degrees centigrade, which is equivalent to 433 degrees Kelvin. Again, I decided to work in Kelvin because of the fluid property library that I'm using. For the purpose of this model, I'm using CoolProp fluid library. For those of you not familiar with CoolProp, CoolProp is a free open source fluid property library where you could access hundreds of fluid properties. Unlike RefProp, CoolProp is free and you can call CoolProp library in MATLAB. If you are interested to know how to set up CoolProp in MATLAB, I've provided a link of my previous video on CoolProp below this video. So back to the R11. Let's assume I want the fluid quality that will be coming out of my boiler to be properly dry vapor. So I'm assuming that the quality of the fluid coming out from the boiler is 1. So I could either specify the quality of the fluid or I could specify the pressure at which this temperature was raised. So whichever one, I could go that route. So let me specify the pressure. Let's say I say P1 is equals, so when I looked at the pressure corresponding to this temperature is about 2484.3 kilopascal. But again, in CoolProp, the unit that it recognizes is for pressure is in Pascal. So you need to reflect your pressures in Pascal and then your temperature in Kelvin. So that's the reason why I decided to work with Kelvin. So the unit should be here, should be Kelvin. And the unit here should be Pascal. or I could specify the quality of the working fluid. Next, let us specify, let's assume this is 0.1, 0.2, 0.3. So we are saying that the fluid is coming out from the turbine and is cooling at 298 Kelvin. So let's say 0.3 and 0.2 would have a temperature of 298. Next, let me specify the organic fluid mass flow. Let me assume 1 kilogram per second. You could specify whatever you like, but for the purpose of this modeling, I'm going to use 1 as a. And then next, let's define the turbine efficiency, and let's call it TURBEF. And let's say it's a modern turbine, and then it has an efficiency of about 0.92. Let's call this turbine efficiency. And with this input for the turbine defined, the next thing we need to do is to quickly find the properties of this fluid at this point. So let's find the enthalpy at that point 1. And let's call it H_1, which is equal to, I need to specify what parameter I'm interested in. So in CoolProp, to do that, you use the inverted comma. I'm interested in the enthalpy, and then I put a comma. Next, you specify what parameters do you need to get that enthalpy. I need the temperature because that's the temperature value I have here. And then you specify the temperature. 433. In other ways, you can either use the 433 or you could specify it as T1. This is how we defined it here. We defined it here as T1. So I'll call it T_1, which is that parameter there. Next, you define either you could use the pressure, you define the pressure, which is corresponding to this, or you could use the quality of the fluid. Whether you use the quality of the fluid or the pressure component, you will still achieve the same result. So let me use the quality of the fluid in this case because I'm assuming that at this point, the dryness fraction is 1. So I'll use 1. So I call it Q, which represents the quality of the fluid. And then I specify that quality in value, which is 1 at vapor, and then 0 is liquid. And then we specify the organic fluid that we are using. In this case, this is R11. Okay, I'll also show you here that if you decide to go the pressure approach, you will still get the same result. So I will just do a test to show you that. So when I copy this, and let's say I paste it, I just want to show you that whether you go the fluid quality route or the pressure route, you still get the same answer. So let's call this test. Let me call it H1 test. And then rather than use the quality of the fluid, I want to use the pressure. So I'll call this pressure now value here is P_1. So this is P_1. Okay, if I just decide to run this, so you will see the result. If I go to Live Editor and then I click on Run, so if you see here, you will notice that I have the same value for enthalpy, whether I use the quality of the fluid or I use the pressure, I still have the same value here. So in CoolProp, you can use the known into the unknown. If you know the quality of the fluid, then you can just right away use the quality of the fluid. If you know if the fluid property is within this dome shape, then you can use that quality. Else, you could just specify the pressure and you will still obtain the same thing. So all through, I'm going to be using the quality since I know that this fluid property is within this dry vapor region. So let's put in the unit. The unit for this is in joules per kilogram. So you're aware of this. This is joules per kilogram. Same as this, joules per kilogram. The next parameter that we could be interested in, because we are going down this way, is the entropy. So I would just again enter the entropy value, and let's also call it S1. But in this case, I'll be using my Q1 because I already know that the property at that level is the quality of the fluid is dry. So I have to change this to X for entropy, and then I change this to S1 for entropy and the same temperature. And then in this case, the unit will be joules per kilogram per Kelvin. So you could also obtain any other parameter that you feel will be relevant to you, but at the point of this modeling, we are only interested in the enthalpy and the entropy at this point. So you could also obtain the density. So let's say if you want the density, you again do same process, and then let's call it D1. I'm not going to use this, but just for your own use. So for density is put in here as D, and the unit for the density here is kilogram per meter cube. Yeah. Then again, you could decide to find the liquid property of the fluid at this temperature. Next, we need to find the thermodynamic properties at point 2. So let's call these thermodynamic properties at point 1. And we need to find the thermodynamic properties at point 2. To do this, there are two approaches. You could either use the entropy quality relationship. Since you know the entropy at this point, you could use that relationship to find the enthalpy value at this point. And to do that, what you need to do is to get the entropy value at the liquid phase here, which you can get since you know the temperature. And you could also find the entropy at this point, since you know at this point the quality of the fluid is 1. The second approach I would just do is to go straight to using the value of my entropy here. This is a constant entropy process. So it means the entropy at point 1 is equal to the entropy at point 2. And since I know the entropy at point 2, I know the temperature at this region, I could just find the quality of this fluid here. So we'll go straight to find the quality of the fluid at point 2. And let's call this Q2, which is the quality of the fluid, Q_2. So I'll just copy all these here and then paste it here. So because I'm looking for the fluid quality at this point, I'm going to change this to Q. I'm looking for Q, which is the quality of the fluid at point 2. And then I know my temperature. Okay, so we need to specify that temperature. Okay, so quickly I will define that temperature. So let's go and define it. So it is called T3. T3 is equal to 298. Okay, now I'll go straight to T2 because it's T2 I'm interested. T2 is equal to 298. And what else do we know about T2? You could also find the pressure at T2, yeah, and T3. So it's also going to be the same pressure. It's because it's a constant pressure line. So it goes here, constant pressure, and then it heats up. So we can quickly obtain the pressure. Come to think of it, we don't need the pressure to obtain the quality of the fluid. All we need is the temperature. and the entropy. So the entropy at point 2, which is x underscore 2, is equal to the entropy at point 1, s underscore 1. Yeah, with this in mind, we can quickly change this value here to t2 and then change, rather than use q, we're using s since we know s. So I'll change this now to 2. And here I change it to s because I know my entropy at this point, which is equivalent to the entropy at point 1. And then I can put a value here. The entropy at that point is x underscore 2. And with this, I can obtain the quality of the fluid at this point. So knowing the quality of the fluid at this point, I can now find my enthalpy at point 2. Here, this one, there's no unit here, and the unit here is joule per kilogram per Kelvin. So I'm looking now for my H2, which is, I'm pasting it here. Yeah, so in this case, I'm looking for the enthalpy now. And I know my temperature, which is T2, and I know the quality of the fluid now at this point. So I'm going to change this to Q, and then this will become Q underscore 2. So with this, I can obtain the enthalpy at that point. And again, the unit is joule per kilogram. So with this, we now have the fluid property that we're interested in at point 2. Then next we go to point 3 to find out the fluid properties at point 3. So what do we know at point 3? At point 3, we know T3 to be 298. We know T3 to be 298 Kelvin. What else do we know at T3? Yeah, we can now obtain the pressure at point 3. So let's call that pressure, which is saturation pressure at the liquid phase. Let's call it P3, which is equal to, again, let me copy this and paste it here. So I know that the quality of the fluid at this point 3 is 0. So I would change this to 0, 0. And because I'm looking for the pressure, I change this to P. And because I already know what the temperature is at that point, then with this I can obtain my P3. Then what else are we interested in? We're interested in finding the entropy at point 3. So we call this again. I'll paste the same thing here, and then I change this to S. So here I know my temperature, I know my fluid quality to be 0, and that's it. Do we need that? Okay, we don't really need the entropy value, but just for your own example, you could have that there. Next, I'm interested in the density of the fluid here because I want to find the specific volume, and in CoolProp, you can find the specific volume using the relationship of density and specific volume. So I would call this here D3 as the specific volume. So the specific volume will be D. Sorry, the density will be D. So this is density because that's what I can obtain here. And again, they should be at the fluid quality of 0. And once I know my density at that point, I can find the specific volume. So the specific volume will be, the specific volume at point 3 will be the inverse of the density. Let's put the units properly. So this will be meter cube kilogram. Here will be kilogram meter cube. So with this in mind now, we can now find the properties at point 4. At point 4. But before we find the properties at point 4, we need to find the enthalpy at point 3. We've not done that. So we need to find the enthalpy at point 3. So the enthalpy at point 3 will be, again, I know this, and then I know the quality of the fluid at that point to be 0. So with this, I now have my enthalpy value at point 3. So we need to change this to Pascal. That's the unit here. And all our units looks okay. Then once we've done this, then we can look for the properties at point 4. Point 4. So what do we know at point 4? At least at point 4, we know what the pressure is, because this is the pressure that the pump raises into the boiler. So it's going to be the same thing as your... So we know the pressure at point 4, which is going to be the same as the pressure that is going into the turbine. So that's the pressure that the pump raises into the boiler, and this is a constant pressure process before going into the turbine. What we don't know at point 2 is the temperature. So because we don't know the temperature, I decided to go through the route of using the specific volume in order to find the properties at point 4. So let's specify the knowns here. So P3, P4, P underscore 4 is the same as P underscore 1. And the unit for this is Pascal. So to find P, the enthalpy at point 4, recall that the pump work here is a function of the organic mass flow, and the temperature, the enthalpy difference at point 4 and 3, which is equivalent to the specific volume against the pressure difference of point 4 and point 3. So with this in mind, we could find the pump work from point 3 up at point 4. So we could say pump work is equals SV underscore 3 times P4 minus P underscore 3. And then with the value of the pump work, we can now find H underscore 4, which is H underscore 3 plus PW. And again, our unit here will be joules per kilogram. So with this, we now have all the parameters that we're interested in. Then we can now start calculating the performance indices. We calculate the heat input, calculate the turbine work. We've already done the pump work. We can now calculate the shaft output power, the efficiency, and that's it. So performance. So first I want to calculate the heat input. The heat input. So the heat input becomes the mass flow of the organic Rankine cycle multiplied by H_1 minus H_4, and the turbine work is mass flow into H_1 minus H_2. So H_2. We already know the pump work. And then the shaft output power becomes the turbine work minus the pump work. Again, here we missed the efficiencies. So here we specify that the turbine efficiency is 0.92. So we could apply that turbine efficiency into this. So we could say here it becomes this parameter times the turbine efficiency. Again, we could also specify the pump efficiency if we need to do that. So let's say pump efficiency is, so let me specify that here. So let me call that here and say pump efficiency is, let's say 0.89, which is 89%. And then we could have that here as specific work divided by the pump efficiency. So we call it pump efficiency. So here, let me use the right parameter or variable. We defined it, so we called it tub efficiency, so you don't get confused about that. Yeah. And then we have the cycle efficiency becomes the SOP divided by HI. So let's add some units here. We may start this one. So this will be in joule per kilogram. And I copy this. Joule per kilogram. Joule per kilogram. Joules per kilogram. And this is the model for R11. You could go ahead to do other calculations you want to do. If you want to do the work ratio, you want to do other calculations, you could do that. I can now run this simulation for R11. So let me go and click on run. And it's running, and we can now see all the parameters with an efficiency of 21.89%. And this is how you develop the model for yourself. Very easy. You don't need much skills in MATLAB to do this. So we'll just jump into the R245fa immediately. So this is my R245fa. You see the dumbbell shape look different from the R11. So in this case, we have some specified temperature and pressure. Let's say we are using the same temperature that is being fed into the turbine. But here, rather than use the same pressure, we have been told that the pressure at which the fluid was going into the turbine, which is the boiler exit pressure, was 33.3 bar. And the temperature is 433. So if you look at this fluid, its critical point is at 427 Kelvin, somewhere around here. And its critical pressure is 36.5 bar. So what this means that this fluid is being raised to 33.3 bar to heat it at 433 temperature. So that means this fluid is at supercritical gas region. It's off the saturated liquid and saturated vapor line. So it's at the supercritical gas phase. So in order to heat this again back to, let's assume that the condenser temperature is 298. So we need to track it down from this point, and then we get the closest point to the dome, which is at the dry vapor, which is VR 0.2, and then this will be our 0.3 and 0.4. So this then brings me to CoolProp, how you can find this fluid property at this region. If you look at these sets of strings, if the fluid property is at a pressure which is below its critical pressure and a temperature below its critical temperature, and which is above its saturation line, then you can use liquid for each string. And if it's a two-phase, you just follow all these criteria here. But if you look carefully here, this fluid is a supercritical gas phase. So you have P, which is less than the critical pressure of this fluid, and the temperature is above its critical temperature. So the temperature we are coming in here is 433, which is above 427. The pressure is 33 bar, which is less than 36.5 bar. So we need to find the thermodynamic properties at this point. So what we're going to do here is we're going to go back to our previous work here. So let's change all these parameters. So we have the pressure here now at 33.3 bar. So this is 33.3 bar. So which we have to change it to Pascal. So that's it. That's 33.3 bar, which is 3,330 kilopascal. So with this, let's assume we have the same turbine efficiency, we have the same mass. So in this case, we need to, because this is not within the fluid quality line, so we need to use the pressure to get the thermodynamic properties at 0.1. So to do this, my H1 now becomes, rather than use Q, I will use P. So let me take this off. So let me delete this, take this off. And since I have pressure already here, I can call this now my P1, and then I can change this fluid to 245fa. Now, interestingly, like I said, this fluid is at supercritical gas region. So I would change these to supercritical. So I would change these to supercritical gas. Again, if you are not sure of the region that you are in, you could just specify it as not imposed. When you use not imposed, CoolProp will determine the phase for you. But if you know the specific phase that the fluid is at that moment, you could specify that phase. So for this, I know this is a supercritical gas region, and I can now use that. So yeah, so if we try to use this, you see you still get the same result. So let me try out something here and show you that you still get the same result. So if I decide to make this, let's call this test. I want CoolProp to determine the phase. So rather than use supercritical, I could use not imposed. And CoolProp will determine that for me. Run this. So before we run this, let me just clear out this results that we have here. Now that I have it clear, I can now run this, and then you will see that both results will be the same thing. So again, if you look at here, you see H1 and H test still gives you the same value. So CoolProp is able to pick the phase of that fluid at that point and was able to compute the result. So now that we know H1, what other parameters that we need to know here? Again, the same way we did in the previous one, we need to find S1, we need to find other parameters depending if you need them. Yeah, so all I need now is S1. So I agree at this, and then I could go either way, either supercritical or superimposed or not imposed. So I'm going to use my supercritical. So I clean up this. And this is my P1, and this fluid is changed to 245. Do I need a density? If you need a density, you could go ahead and do that, but I don't think we'll need a density at that point. Yeah, so what else do we need? Then we move to point 2. What do we need in point 2? Luckily for us, the point 2 is at saturated vapor and at a dryness fraction of 1. So we come here to point 2. Again, we know the temperature at point 2 to be 298, which is same thing. So I would open up this one, point 2. Temperature is 298. The entropy at point 2 is same as point 1. So entropy at point 2, same as point 1. The quality of the fluid we already know, so we don't need this anymore. So I'll just take this off. We don't need this because we already know the quality is 1. And since we know the quality to be 1, so we can find the enthalpy now. And here we can change this to be 1. And then we change this fluid to be 245fa. With this, we know both properties here, and we don't need the entropy anyway. And yeah, So with that, then we go to point 3. Again, at point 3, let's assume the pump efficiency remains the same. And then we know that T3 is 298. We can find P3. So P3 will be the same as previous, because we know the temperature at that point, which is 298, and the quality of the fluid at point 3 is 0. And then we just change this fluid to 245fa. Next is the entropy. Do we need the entropy? No, we don't need the entropy to do our calculation, so I wouldn't bother going through that route. I'll just take it off. Do we need the density? Yes, we need the density in order to calculate the pump work. So we could go the same process and then do the density, and then we change this fluid to 245fa. Yeah. Do we need the specific volume? Yes, we need the specific volume. So I change this, and yeah, that's it. And then do we need the enthalpy? Yes, we need to calculate the enthalpy. Again, we change this fluid to 245fa. Next, we move to point 4. Again, the same process, point 4. P4 is equal to P1. And then the pump work is going to be, but again, the same relationship as in the previous example. And H4 is going to be as the same relationship in the previous example. And with that, we are able to get all the thermodynamic properties of the fluid at a different points. And then we can go straight away to calculate the performance. And it's going to be the same. And we already have all our units intact. And that's it. And with this, you are able to compute your efficiency for R245a. Let's say peradventure you have this pressure somewhere and it's going around this direction, and rather than go straight to hit this point at this dome here, you could decide to hit somewhere here and you have the pressure come up this way. Yeah. Again, let me run. Hope everything is correct here. So I can now run this model to see what the efficiency of this fluid is. And again, the efficiency is there, 28.68%, and that's the efficiency for the R245fa. And with this, you can now model R11 and R245fa Organic Rankine Cycle. I hope you find this video useful and you now know how to model Organic Rankine Cycle with R11 or R245fa organic fluid. If this video was useful to you, please hit the like button and subscribe. Also, hit notification icon so you can get notified each time I upload a new video. If you have any topic on MATLAB that you want me to cover, please feel free to leave a comment in the comment section below. Thank you for watching and see you in my next video. Bye for now.